Chapter 8, talking about alkyl halides and the second type of reactions they undergo, which are called elimination reactions. So let's have a quick comparison between the substitution and elimination reactions. In substitution reactions, as we saw in the previous chapter, we need a nucleophile. We have the substitution of the halogen, fluorine, chlorine, bromine, and iodine. We learned that chlorine, bromine, and iodine are the best. And the product is a substituted product. Nucleophile is going to replace the halogen. But what happens in elimination? The name describes eliminate. Elimination happens instead of a nucleophile, we have a base. It starts with extraction of hydrogen. And the final product is an alkene. We will learn about everything about alkenes next time, their nomenclature, their reactions, but today we are going to produce them. So let's learn a little bit about alkenes as far as just the stability and the structure. So what we need here is to know about the substituents on the double bond. Just do this. Smaller. Fortunately, the board is not large enough. So you see both of the carbons of double bond only are connected to hydrogen here. Then we'll start replacing the hydrogens with an alkyl group. Alkyl groups, combination of carbon and hydrogen, right? So one alkyl group, then two alkyl groups, and you can have another substituted. Let me draw them here because I'm going to explain everything on these structures. And finally, with three substituents here. And lastly, all right, so let's learn about their names. No substitution, mono substituted, these are di-substituted, this is a tri-substituted alkene, and this is a tetra substituted. What do we mean by the substituted? Pay attention to carbons of double bond. Do you see anything except hydrogen here? No. So there is no substitution, no substitution. Here on the carbon of double bond, one of the carbons of double bond is connected to one more carbon here, so we call it a monosubstituted. In these two structures, we have carbons of double bond to substituted, and to the substitutions, to the carbons. This carbon to one, this carbon to another one, so 1 and 1 is 2. Now, why do we have two different types of structures? If the two substitute parts are on the same side, we call it cis. If the two substituted parts, two substitutions, are on the opposite sides of the molecule, we call it trans. So keep it in mind, We will work more with them in the next chapter, but you need to know them here right now. So when the two substitutions, when the two carbons connected to carbons of double bond are on the same side of the molecule, we call them cis. When the substitutions, the carbons connected to carbons of double bond are on two sides, we call them trans. And in a few minutes, you will see some exercises about them to make sure we understood. If there are three carbons connected to carbons of double bond, it's called a tri-substituted alkene. And finally, if all of the bonds around the carbons of double bond are connected to the carbons, we call it tetra-substituted. Now, as far as the stability, because we need to know the stability, sometimes we need to figure out which product is the major product. As far as the stability, the more substitution, the more stable alkene. So, the alkene with no substitution is the least stable. Then by increasing the substitutions, you will have more stability. Stability of trans is more than cis, and the tetra-substituted is the most stable. Now, you may ask why is that? It's because by increasing the alkyl groups, means we have carbon and hydrogens, we have a better flow of electrons over double bonds, and trans more than cis, again the same, but a symmetrical flow of electrons, just a distribution of the charges. That's all you need to know about it, but you need to know this trend for the stability. No substitution is the least stable, and the most substitution, tetra-substitution, is the most stable. All right, now let's classify some of the alkenes given to us on page 1 of this study guide, and classify the carbons as far as the number of their substituents. I will work on A, you can work on B. So we'll work on vitamin A together, you will work on vitamin D3. So page 1, vitamin A is a very long molecule, but we can draw it fast thanks to the skeletal structure. That's the vitamin A. Good for eyesight. Let's see how many. 1, 2, 3, 4. 1, 2, 3, and 4. Okay, let's classify each of these by the number of carbons bonded to double bond, or let's try monosubstituted, tri-substituted. So seems like we need another color. Let's start with this double bond. The carbons of double bond here are this carbon and this carbon, right? So connecting to this carbon, we have this carbon and this carbon, right? Two substituents here. Connected to this carbon, we have this and this. So it's a tetra-substituted. Or if we want to just put, I don't want it to be too crowded, let me just write down the number of carbons connected to these. There are 4. I write it on this double bond to show that 4 carbons are connected to these 2 carbons. Now, for the second double bond, you see on this carbon, you have, you're talking about these 2 carbons, right? On this carbon, you have 1, 2, 3 bonds. The last one is a hydrogen. So, again, we have 1 here, right? And we have another hydrogen here, correct? Because this carbon also has 3 bonds. So, we have 1 group here and 1 group here. Can I say 2? Here, next double bond. We're talking about these two carbons, one here group, one group here, and on the next carbon there is a hydrogen missing. So we're just talking about this group connected, right? Any connection except the carbon-carbon double bond, right? Pay attention, don't get confused. We are not counting the double bond, just the groups on the carbons of double bond. So we have two here again. Next one, one and two carbons here. And if you count the groups, there is a hydrogen missing on each one. We are not counting the hydrogens, so there is one already here, and there is one here, again, two. And finally, the last double bond, we're talking about these two carbons. This carbon has 4 bonds already, but this one has a hydrogen. So, on this carbon, the left side, you see 2 carbon-carbon bonds, but on this carbon, you have 1 carbon-carbon bond. So, there are 3. That's how you classify the type of carbons. I classified each double bond. If you want to classify on each carbon, then you would say, instead of each double bond, you would say 2 here, you would say 2 here, and then you would say 1 here on this carbon, you would say 1 here on this carbon, and on this carbon you would say 1, 2, and here you say 1. On this carbon you would say 1. On this carbon, instead of bond now, I'm doing 1 by 1. So on this carbon you will say just 1. On this carbon you would say 2. On this carbon. And finally on this carbon you would say 1. So it's better to go with carbon by carbon, but even if you do the total bond, depending on if you are talking about the exam, depending on what the question is asking. One more thing about the cis and trans is that so what did we say about, no, there's no hydrogen here. What did we say about the structure of this one? This is cis, right? And this is a trans. Alkyl groups, the carbons on one side, the carbons of double bonds are on 2 sides. But don't forget that there is no rotation around the double bond. There is no rotation. Pay attention to this. No sign. So it means that don't think that and don't assume that just like the single bond, these double bonds can rotate. Nothing. Let's move towards page 2. This question says, for which double bond are stereoisomers possible? Means if we can have cis or trans or any other stereoisomers. Before we do that, let me explain something else one more time. On cis or trans, we should have at least to this moment, to this point, right? We should add something else in the next chapter. Each carbon of double bond must have 1 hydrogen. Okay? This is cis, this is trans. And we call them stereoisomers. Stereoisomers. So, for example, if a carbon is connected to 2 same carbons, this carbon is connected to methyl groups, right? There is no stereochemistry around this carbon. No stereo. stereoisomers. You remember we said the carbon, which is connected to 4 different groups. This carbon has a stereochemistry because it's connected to a hydrogen, but not this one. Okay? So that's what we are going to determine in this exercise. I'm working on part B. So, look what I told you. Doesn't it look like this? This carbon is connected to 2 methyl groups, 2 same groups. So there is no stereochemistry here. Here, the 4th bond is hydrogen, correct? Here, hydrogen. So, since the question is asking which double bond has a stereoisomer, so let's look at this. Here, we did not have a stereoisomer. Here, we have 4 different groups, right? So, we have stereo. We can have cis and trans around it. All right, I hope it was clear. Can work on C also. Okay. Now, this carbon and this carbon. On this carbon, there are 2 different groups. But on this carbon, you see this half of the molecule is the same as the half of molecule. Don't get confused when you have a cyclic compound connected. It's like you are cutting it in half, and you will see the 2 sides are exactly the same, as if like 2 same groups, identical groups are connected to this carbon. But if you had a substituent here, like a methyl group or OH group here, then the 2 sides wouldn't be the same. So there is no stereochemistry on this double bond, no, because these 2 sides of this cyclohexane are the same. But on this double bond, let's see what happens. On this carbon, we have a hydrogen, right? So we obviously have 2 different groups, hydrogen and a methyl. Here we have this group and the rest of the molecules, so we have a stereochemistry here. Basically, you must have 4 different groups around both of the carbons to call for a stereoisomer and having a stereochemistry. All right, so let's work on the next exercise, determining cis and trans. At this point, you should be able to see and distinguish the cis and trans and say which one is more stable. The 2 pairs are given to you. So the 2 alkyl groups are on the same side of the bond. So this is cis. The 2 alkyl groups are on the 2 opposite sides because these are hydrogen and hydrogen, right? So this is trans. Between cis and trans, which one did we say is more stable? Trans, because of the distribution, the weight of the distribution of the charges and the flow of electrons. On the cyclic compounds is the same, just needs a good visualization. I don't want you to get confused on the cyclic compounds, on the rings. All right, let's see what it is. You see the two alkyl groups on the same side. So this is cis, and this one we have 2 hydrogens on the same side, so alkyl groups are on the same side as well. Okay, so this is cis also. It's time to introduce Zaitsev's rule. Zaitsev's rule. Russian scientists were very strong and active on organic chemistry at some point, so you will learn a few of them in the name of them in organic chemistry. Zaitsev's rule. So, or let me wait for the Zaitsev rule. I don't want to confuse you. That's fine. Sorry, but we will talk about it as soon as we introduce the elimination reactions. So, what is the difference between this cis and this cis? Now we need a tiebreaker. We go with the number of substituents on the double bond. On this double bond, you have 1, 2, and 3, right? 3 substituents total. Or let's say it's tri-substituted. Substituted. You see that? 1, 2, 3. Here you have 1 and 2 because others are hydrogens, so it's a di-substituted. Between di-substituted and tri-substituted, which one is the winner? Tri-substituted, right? We just learned about the stability. Okay. Now we're still on page 2. We are classifying each double bond based on the substitution. Let's work on A first. On A, the number of substituents on double bond. 1, 2, and 3. Don't forget, we are not counting hydrogens. So total 3. For B, here we have 1 substituent, and this is hydrogen. Do you see any alkyl groups here? No, means there are 2 hydrogens. So how many do you see here? Only 1. For C, on this carbon you see 1 and 2. On this carbon you just see 2 hydrogens. So it's 2. On D, so on this carbon, you have 2. On this carbon, you also have 2. So how many total? 4. And if, for example, you want to determine the trend of their stability, 4 is the most stable, then the 3, then the 2, and then 1. Okay. Work on these basic concepts and stability of alkenes. In the next video, we are going to go over the 2 different types of elimination reactions and some practice on each.